There is a speed limit built into reality, and it is not a guideline. It is a boundary written into the equations of special relativity, a constraint so absolute that crossing it would unravel the structure of space-time itself. That limit is the speed of light, exactly 299,792,458 meters per second, and every massless particle in the universe is locked to it with perfect precision. This is not just a property of light, it is a property of reality. The deeper reason lies in the geometry of space-time, governed by the Lorentz transformation. As any object with mass accelerates toward this limit, its energy rises without bound, while time slows and distances contract. The closer you get, the more extreme these effects become, until reaching the limit would require infinite energy. And here is the unsettling part. You are not stationary. You are already moving through space-time at this ultimate speed, just not in the way you expect. The speed limit, written into the fabric of reality. To understand why the speed of light functions as an absolute cosmic speed limit, it is necessary to first understand what kind of limit it is. It is not a speed limit in the engineering sense, the way a car's top speed is limited by friction, air resistance, and engine power. Remove those constraints and the car goes faster. The speed of light is a limit in the mathematical sense, the way the number 1 is the limit of the series 1/2, 3/4, 7/8, 15/16. You can approach it without bound. You can add as many terms as you like, get as close as you like, but the limit itself is never reached, and no amount of additional effort closes the remaining gap. The key to understanding this is the concept of space-time. In Newtonian physics, the physics that governed all scientific thinking before Einstein's 1905 paper on special relativity, space and time, were completely separate things. Space was a three-dimensional arena in which events occurred. Time was a universal clock that ticked at the same rate for everyone everywhere, regardless of motion or position or any other physical circumstance. These two things did not interact. They were independent backdrops against which the drama of physics played out. Einstein destroyed this picture. His special theory of relativity, derived from two deceptively simple postulates, revealed that space and time are not separate things. They are two aspects of a single four-dimensional structure called space-time. The three dimensions of space and the single dimension of time are woven together into a unified fabric, and the way they are woven together is governed by a single number, the speed of light. The speed of light is not just the speed of light, it is the conversion factor between the space dimensions and the time dimension of the universe. It is the rate at which the universe translates motion through space into effects on the passage of time. It is built into the geometry of the four-dimensional structure of reality at the most fundamental level. This is what makes the speed of light a genuinely different kind of limit. When you drive a car, you are moving through the three spatial dimensions of space-time. The time dimension continues to flow at roughly 1 second per second for you and for everyone else. At everyday velocities, the interaction between your spatial motion and the time dimension is so small as to be completely undetectable. But the interaction is always there. Every object moving through space is simultaneously moving through time, and these two motions are connected by the structure of space-time in a way that has consequences that become dramatic as spatial velocity increases. The speed of light is the universal speed through space-time. Every object in the universe, moving or stationary, is moving through the four-dimensional structure of space-time at exactly the speed of light. This is not a metaphor or a loose analogy. It is a precise mathematical statement. Stationary objects direct all of their space-time velocity into the time dimension. They move through time at the maximum rate, 1 second per second in their own reference frame. Objects moving through space trade some of their temporal velocity for spatial velocity, and the exchange rate is governed by the structure of space-time and characterized by the speed of light. As an object moves faster through space, it moves slower through time. The total velocity through space-time remains constant at the speed of light. The only thing that changes is how that fixed budget of space-time velocity is allocated between spatial and temporal motion. The implications of this are extraordinary. If you want to move faster through space, you must sacrifice a velocity through time. The faster you go through space, the slower time passes for you relative to observers who are stationary. At everyday speeds, this effect is too small to measure without extremely precise instruments. But it is always present, and as spatial velocity increases, it becomes progressively more dramatic. At the speed of light, the entire space-time velocity budget would be directed into spatial motion, leaving nothing for temporal motion. Time would stop completely, and because matter cannot exist without time flowing, because every atomic process, every chemical reaction, every thought and heartbeat requires the passage of time, it is impossible for any massive object to reach the speed of light. Doing so would require the cessation of time, and without time, the object could not exist. The man who broke physics with a thought experiment. Albert Einstein was 26 years old and working as a patent clerk in Bern, Switzerland, when he submitted the paper that would become known as the special theory of relativity. The year was 1905, and Einstein had no academic position, no access to laboratory equipment, no collaborators of particular note, and no resources beyond his own mind and the mathematics he had taught himself. What he had was a question that had been bothering him since the age of 16, a question that seemed simple, but whose answer turned out to be one of the most consequential pieces of reasoning in the history of science. The question was this: what would a beam of light look like if you could ride alongside it at the same speed? According to the physics of James Clerk Maxwell, who had unified electricity and magnetism into a single theory of electromagnetism in the 1860s, light was an electromagnetic wave traveling through empty space at a specific speed determined by the properties of electric and magnetic fields. Maxwell's equations predicted this speed with extraordinary precision, and it matched the measured speed of light perfectly. But Maxwell's equations said nothing about who was measuring the speed. They gave the speed of light as a fixed number, with no reference to any particular observer. This created a problem. According to the classical Newtonian physics that had dominated scientific thinking for 2 centuries, velocities add. If you are on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, a stationary observer sees the ball moving at 150 kilometers per hour. Relative to the ground, your emotion and the ball's motion add together. This seems obvious, and it works perfectly for every everyday experience. But if it applies to light, then the speed of light should appear different to observers in different states of motion. An observer moving away from a light source should see the light catching up to them more slowly than an observer standing still. An observer moving toward the source should see it approaching faster. But Maxwell's equations gave no hint of any such variation. The speed of light appeared in those equations as a single constant, with no dependence on the motion of either the source or the observer. And the thought experiment that Einstein had been pursuing since age 16 made the problem concrete in a way that was deeply unsettling. If you travelled alongside a beam of light at exactly the speed of light, you would see the electromagnetic wave frozen in space ahead of you, oscillating but not propagating. But Maxwell's equations have no solution that describes a frozen electromagnetic wave. Such a thing cannot exist according to the mathematics of electromagnetism. The thought experiment led to a contradiction. Einstein's resolution was radical and took years of thinking to fully develop. Rather than assuming that velocities add in the simple Newtonian way and trying to reconcile this with Maxwell's equations, Einstein asked what would happen if he simply assumed that the speed of light is the same for all observers regardless of motion. This assumption, which seemed to fly in the face of common sense, turned out to be consistent with Maxwell's equations. The question was what else it would require. The answer was that almost everything about the Newtonian picture of the world would need to change. If the speed of light is always the same for all observers, regardless of their relative motion, then time cannot be absolute. Two observers in relative motion will measure different amounts of time elapsing between the same pair of events. Neither measurement is wrong. Both are correct descriptions of the same physical reality from different reference frames. Space cannot be absolute either. Lengths measured along the direction of motion will be different for observers in relative motion. Simultaneity, the concept of two events happening at the same time, will depend on the reference frame of the observer. All of these consequences follow necessarily and mathematically from the single assumption that the speed of light is constant for all observers. Einstein did not add them separately. They emerge from the logic alone. The mathematic that describes this structure is called the Lorentz transformation, and it had actually been derived before Einstein by the Dutch physicist Hendrik Lorentz, who was trying to explain puzzling experimental results without abandoning the Newtonian framework. Lorentz thought of it as a mathematical trick with no deeper physical meaning. Einstein recognized it as the correct description of the geometry of space-time. That distinction between a mathematical convenience and a physical reality was the conceptual leap that changed everything. The consequences for the speed of light as a physical limit emerged directly from this framework. If the speed of light is always the same for all observers, then nothing moving through space can ever appear to match it, because an observer traveling alongside the light at the same speed would measure the light moving away from them at the full speed of light, which contradicts the premise that they are moving alongside it. The constancy of the speed of light and the impossibility of reaching it are not two separate facts. They are the same fact described from different angles. The speed limit is not imposed on top of the structure of space-time. It is the structure of space-time, expressed as a maximum velocity. The Lorentz factor and the mathematical demon that ends all hope. The heart of special relativity, the number that quantifies everything that goes wrong as an object approaches the speed of light, is called the Lorentz factor. It appears in every relativistic equation that describes how time, length, momentum, and energy change with velocity. It is a single mathematical expression, but it encodes the entire catastrophe of trying to reach the speed of light, and examining what it does to physical quantities as velocity increases is the clearest way to see why the speed limit is truly absolute, rather than merely very difficult. The Lorentz factor is written as gamma, and its formula is straightforward. It is 1 divided by the square root of 1 minus the square of the velocity divided by the square of the speed of light. At 0 velocity, gamma equals exactly 1. At low velocities, gamma stays very close to 1. A car travelling at 100 kilometers per hour has a gamma of approximately 1 plus 2 times 10 to the negative 15th power. The deviation from 1 is so small that it would take a precision measurement lasting billions of years to detect the difference. For all practical purposes at everyday speeds, gamma is 1 and special relativistic effects are completely invisible. This changes as velocity increases toward the speed of light. At 10% of light speed, gamma reaches approximately 1.005, still barely noticeable. At 50% of light speed, gamma is approximately 1.155. Now effects are measurable, time running about 13% slower for the moving object than for a stationary observer. At 90% of light speed, gamma jumps to approximately 2.29. Time runs at less than half the rate. At 99% of light speed, gamma reaches approximately 7.09. At 99.9%, it reaches approximately 22.4. At 99.99%, approximately 70.7. At 99.999%, approximately 223.6. The pattern is unmistakable, and it is the key to understanding the speed limit. As velocity approaches the speed of light, the Lorentz factor does not merely grow, it grows without bound. There is no finite value of gamma that corresponds to exactly the speed of light. At exactly the speed of light, the denominator of the Lorentz factor formula becomes the square root of 1 minus 1, which is the square root of 0, which is 0. Dividing 1 by 0 does not give a large number. It gives an undefined quantity. The mathematics breaks down entirely. The equation has no solution at light speed for any massive object, because the Lorentz factor at light speed is not infinity. It is undefined. This distinction matters. An undefined Lorentz factor is not the same as an infinite one. An infinite Lorentz factor would mean that physical quantities like momentum and energy became infinite at light speed. An undefined Lorentz factor means that the equations themselves cannot even be written at light speed for massive objects. The physics does not predict catastrophically large numbers at light speed. It predicts nothing at all, because the framework within which the prediction would be made ceases to be applicable. Every physical quantity that the Lorentz factor multiplies or divides becomes correspondingly impossible to define at light speed. The time dilation factor, the length contraction factor, the relativistic momentum, the total relativistic energy, all of them are functions of gamma, and all of them become undefined when gamma becomes undefined. The universe is not saying that reaching the speed of light would require infinite resources. It is saying that the concept of a massive object at the speed of light is not a physically meaningful concept in the first place. There is no state to be in. There is no value of the physical quantities that would describe such an object. The speed limit is not a wall that blocks passage. It is an edge beyond which the territory does not exist. Understanding this is crucial because it shows why no technological advance can change the situation. The problem is not that current rocket engines are not powerful enough. The problem is not that we have not yet discovered the right fuel. The problem is not one of resources or ingenuity or scale of effort. The problem is that the mathematical framework that describes physics, tested to extraordinary precision by every experiment ever conducted, simply does not contain a description of a massive object at the speed of light. Reaching it would not be like climbing an extremely tall mountain, where you can always add more effort and get a bit higher. It would be like climbing a mountain that ends not at a summit, but at a boundary beyond which the concept of altitude ceases to have meaning. Why momentum becomes your worst enemy. In Newtonian mechanics, momentum is a simple concept. It is mass multiplied by velocity. A bowling ball moving at 10 meters per second has a specific momentum. Double the velocity and you double the momentum. Apply a force for a given time and the momentum changes by the force times the time. The relationship is linear and intuitive. More force produces more acceleration. Doubling the applied force doubles the rate of momentum change. The math is clean and predictable, and it works perfectly for everything that moves at ordinary speeds. Special relativity reveals that this simple picture is an approximation, valid when velocities are small compared to the speed of light, but increasingly inaccurate as velocities grow. The relativistic formula for momentum is not simply mass times velocity. It is mass times velocity times the Lorentz factor gamma. At low velocities, gamma is essentially 1, and the formula reduces to the Newtonian version. But as velocity increases, gamma increases, and the momentum grows faster than velocity alone would suggest. At 90% of the speed of light, gamma is approximately 2.29. An object moving at this speed has momentum 2.29 times larger than the Newtonian formula would predict. To accelerate this object further, you must overcome not just the resistance implied by its rest mass, but the resistance implied by its current relativistic momentum, which is already more than twice what classical physics would suggest. The object behaves as if it were much more massive than it actually is, in the sense that it resists acceleration much more strongly, even though its actual mass measured at rest has not changed at all. Push to 99% of light speed, and gamma rises to 7.09. The object's momentum is 7 times the Newtonian prediction. Accelerating it even slightly requires 7 times more force than the classical formula would indicate. Each small increment of additional velocity requires correspondingly more force than the previous increment. Not proportionally more, but exponentially more. The relationship between applied force and achieved acceleration is no longer linear. It is governed by the Lorentz factor, which is rising rapidly as velocity approaches its limit. The physical picture that emerges from this is of an object that becomes progressively harder to accelerate, not because its mass is increasing in any conventional sense, but because the geometry of space-time makes each additional increment of velocity increasingly expensive in terms of momentum change. The momentum of a massive object at the speed of light would be gamma times mass times the speed of light, and since gamma is undefined at the speed of light, so is the momentum. There is no well-defined momentum state corresponding to a massive object at light speed. Getting there would require achieving an undefined momentum, which is not achievable by any finite series of finite forces applied for finite times. The particle accelerators that humanity has built provide the most direct experimental confirmation of relativistic momentum. The Large Hadron Collider accelerates protons to approximately 99.9999991% of the speed of light. At this velocity, the Lorentz factor is approximately 7,460. The proton's relativistic momentum is 7,460 times larger than classical mechanics would predict for particles moving at that speed. The magnets of the collider must exert forces calibrated to the relativistic momentum, not the classical momentum. If the accelerator were designed using classical momentum formulas, it would fail to keep the protons on their circular track. The fact that the accelerator works, and works with extraordinary precision, is direct experimental proof that relativistic momentum behaves exactly as the Lorentz factor predicts. What happens when two protons collide at these velocities is equally instructive. Their kinetic energy, stored in their relativistic momentum, is so enormous that in the collision, it can materialize as new particles, quarks, gluons, W and Z bosons, Higgs bosons. These particles did not exist before the collision. They are created from the energy of the collision, according to the same equation that relates mass and energy. This is not a hypothetical or a theoretical prediction. It is observed millions of times per second in the Large Hadron Collider. The relativistic momentum of the colliding protons is converted into the mass of new particles with perfect consistency with Einstein's equations. The confirmation of the theory is not indirect or circumstantial. It is as direct as science gets. The energy numbers that kill every dream of light-speed travel. The energy required to accelerate a massive object to the speed of light is not large. It is not extremely large. It is not astronomical. It is infinite. This is the statement that special relativity makes, and it makes it precisely and unambiguously through the formula for relativistic kinetic energy. Understanding the practical implications of this statement requires looking at the numbers for realistic scenarios, because even before reaching infinity, the energy requirements become so catastrophically large that they exceed the total energy available in the solar system by many orders of magnitude. Start with a modest spacecraft, 1,000 kilograms, approximately the mass of a small car. This is not a large interstellar vessel. It is a tiny capsule, perhaps capable of carrying a single person with minimal life support. The goal is to accelerate this capsule to 99% of the speed of light. The relativistic kinetic energy formula gives the result. At 99% light speed with a Lorentz factor of approximately 7.09, the kinetic energy of this 1,000 kilogram object is approximately 5.7 times 10 to the 20th joules. To give this number scale, the total energy released by the most powerful nuclear weapon ever detonated, the Soviet Tsar Bomba, was approximately 2.1 times 10 to the 17th joules. The kinetic energy of the 1,000 kilogram spacecraft at 99% light speed is approximately 2,700 Tsar Bombas worth of energy. For a capsule the mass of a small car, the total annual energy consumption of the entire human civilization, every power plant and every vehicle and every device on Earth for an entire year, is approximately 5.8 times 10 to the 20th joules. The kinetic energy needed to accelerate our 1,000 kilogram spacecraft to 99% light speed is approximately equal to the entire energy production of human civilization for 1 year. And 99% is not the speed of light. It is 1% short of it. Now push to 99.9%. The Lorentz factor rises to approximately 22.4. The kinetic energy rises to approximately 1.9 times 10 to the 21st joules. More than 3 years of total human energy production for the same 1,000 kilogram spacecraft. Push to 99.99%. Lorentz factor approximately 70.7. Kinetic energy approximately 6 times 10 to the 21st joules, roughly 10 years of total human energy production. The pattern is clear and it is devastating. Each additional 9 in the percentage requires roughly 2 to 3 times more energy than all previous acceleration combined. The energy required does not grow linearly or even polynomially with velocity. It grows according to the Lorentz factor, which itself grows without bound. Adding 9s to the decimal of the velocity requires exponentially more energy each time, with no convergence and no ceiling below infinity. At exactly light speed, the kinetic energy formula requires multiplying the rest mass energy by the Lorentz factor -1. Since the Lorentz factor at light speed is undefined rather than infinite, the kinetic energy at light speed is also undefined. But the approach to light speed involves the Lorentz factor growing without bound, so the kinetic energy required grows without bound in the limit. There is no finite amount of energy that would be sufficient to reach light speed exactly. not a large finite amount, not an astronomically large finite amount, no finite amount at all. This energy has to come from somewhere, and wherever it comes from creates additional problems. If the spacecraft carries its fuel, the fuel has mass, and the mass of the fuel requires additional energy to accelerate it alongside the payload, which requires more fuel, which requires more energy. The rocket equation governs this situation, and it produces results that are more brutal than the energy calculation alone. If the energy is beamed to the spacecraft from an external source, the beaming system must handle the enormous power levels involved, which creates engineering challenges of a completely different order. Either way, the energy problem is not a temporary obstacle awaiting a clever solution. It is a fundamental barrier arising from the structure of spacetime and the properties of matter within it. You are already traveling at the speed of light. The statement that every object in the universe is already moving at the speed of light sounds like a paradox, like something deliberately designed to confuse. You are sitting still. You are not moving at 299,792,458 meters per second. You would notice that. And yet the statement is precisely true, and understanding why it is true is the key to understanding the deepest reason why reaching the speed of light through space is impossible. The crucial word is spacetime, not space, spacetime, the four-dimensional structure that combines the three dimensions of space with the dimension of time into a single geometric object. Every event in the universe can be described as a point in spacetime, characterized by four coordinates, three spatial coordinates and one temporal coordinate. An object moving through the universe traces out a path through spacetime called a world line. The world line of a stationary object runs purely along the time dimension. The world line of a moving object runs at an angle, with components in both spatial and temporal dimensions. The velocity of an object through spacetime is a four-dimensional quantity, not a three-dimensional one. It has components in all four dimensions. For massive objects, this four-dimensional velocity has a fixed magnitude determined by the geometry of spacetime and equal to the speed of light. This is not an empirical fact derived from observation. It is a geometric property of the spacetime manifold, analogous to the way that every point on the surface of a sphere is the same distance from the center, regardless of which direction you move along the surface. When you are sitting still in space, your entire four-dimensional spacetime velocity is directed along the time dimension. You move through time at the maximum rate, 1 second of proper time per second. From your own perspective, this feels like time simply passing normally. From the perspective of special relativity, you are moving through the time dimension of spacetime at the speed of light, which is why your four-dimensional spacetime speed equals the speed of light even though your spatial speed is 0. Now imagine you start moving through space. Some of your four-dimensional spacetime velocity is redirected from the time dimension into the spatial dimensions. The magnitude of your four-dimensional velocity remains constant at the speed of light, because that magnitude is fixed by the geometry of spacetime and cannot change. But the direction changes. More of it points spatially, less of it points temporally. As a result, your motion through time slows down. Your clock ticks more slowly than the clocks of observers who remain stationary. This is time dilation, and it is not an optical illusion or a measurement artifact. It is a genuine geometric property of world lines through spacetime. A clock that moves through space traces a longer path through spacetime than a clock that remains stationary, in the same way that a ruler tilted at an angle appears shorter in one dimension than a ruler aligned with that dimension. The tilted ruler is not shorter overall. Its length is just distributed across both dimensions rather than one. Similarly, The moving clock is not experiencing less time overall. It is just distributing its space-time velocity across both spatial and temporal dimensions, rather than only temporal. The implications for reaching light speed are immediate. To move at the speed of light through space would require directing your entire four-dimensional space-time velocity into the spatial dimensions, with nothing left for the temporal dimension. Time would stop completely. Your world line in space-time would become a horizontal line running purely spatially with no temporal component. But a horizontal world line in space-time is not possible for a massive object, because the structure of space-time imposes a constraint on world lines called the time-like constraint. The world lines of massive objects must always have a non-zero component in the time dimension. They cannot be purely spatial. Only massless particles like photons are permitted to have world lines with zero temporal component, and this permission is a geometric property of their zero rest mass, not something that could be achieved by a massive object through the application of sufficient force or energy. The speed of light is not a barrier that a massive object approaches and cannot quite break through. It is a geometric boundary of a different category of world line, a category that massive objects are simply not members of, regardless of their velocity. The universe has a frame rate, and you cannot exceed it. The metaphor of a frame rate is useful for understanding what the speed of light represents at the deepest physical level. A video has a frame rate, the number of discrete images displayed per second. Events in the video can only be separated by time intervals that are multiples of the frame period. If the frame rate is 30 frames per second, nothing in the video can happen faster than 1/30th of a second. The frame rate is a fundamental limit on the temporal resolution of the medium. The speed of light is something analogous for the universe itself, but more fundamental. It is the maximum rate at which a cause in one location can produce an effect in another location. No event can influence another event faster than the time it would take light to travel between them. This is not merely an observation about how light happens to behave. It is a statement about the causal structure of space-time, about what it means for two events to be connected by cause and effect. In special relativity, the set of all events that a given event can causally influence is called its future light cone. It is the set of space-time points that are reachable from the original event by signals traveling at or below the speed of light. Events outside the light cone cannot be influenced by the original event, because reaching them would require a signal to travel faster than light. The light cone is a fundamental geometric feature of space-time, determined entirely by the speed of light and the four-dimensional structure of the universe. The reason the speed of light is the relevant quantity here is that light is massless, and massless particles automatically travel at the maximum possible signal speed in space-time. The maximum signal speed is not light speed, because light happens to be fast. Rather, light travels at the maximum signal speed because it is massless, and the maximum signal speed is determined by the geometry of space-time. If light did not exist, the maximum signal speed would still be the same. It is written into space-time geometry, not into the physics of photons. This understanding makes the speed limit more obviously absolute. It is not that light has been measured to travel at a certain speed, and that speed happens to be a limit. It is that space-time has a causal structure that permits influences to propagate at a maximum rate, and light happens to be one of the entities that propagates at that rate. The speed of light is a measurement of the universe's causal speed, the rate at which cause becomes effect across a distance. Nothing can exceed the causal speed of the universe, because doing so would mean effects preceding causes in some reference frames, which violates the logical structure of reality. The connection between the speed of light and causality also explains why the limit applies universally, regardless of the physics involved. Electromagnetic waves travel at the speed of light because of the structure of Maxwell's equations. Gravitational waves travel at the speed of light because the field equations of general relativity require it. Gluons, the particles that mediate the strong nuclear force, are massless and travel at the speed of light. Any massless particle, regardless of what interaction it mediates, travels at the causal speed of the universe, and any massive particle, because it has rest mass, cannot reach that causal speed without infinite energy. The universality of the speed limit follows from the universality of the causal structure of spacetime. Experiments searching for violations of the speed limit have been conducted with extraordinary precision. In 2011, the OPERA experiment briefly announced that neutrinos appeared to travel faster than light in experiments measuring the travel time of neutrino beams from CERN in Switzerland to the Gran Sasso laboratory in Italy. The announcement was greeted with intense skepticism by the physics community, not because the community was closed-minded, but because the result conflicted with decades of successful verification of special relativity and with observations of supernova 1987A, where the arrival time of neutrinos relative to photons was consistent with neutrinos traveling at effectively the speed of light. The OPERA result was eventually traced to a loose fiber optic cable connection in the timing system that introduced a spurious delay. When the hardware error was corrected, the neutrinos traveled at exactly the expected speed. The speed limit held. It always holds. What the Large Hadron Collider proved about the final barrier. The Large Hadron Collider is a circular tunnel 27 kilometers in circumference straddling the border of France and Switzerland, buried approximately 100 meters underground. Inside this tunnel, two beams of protons travel in opposite directions around the ring, guided by more than 1,200 superconducting magnets cooled to approximately 1.9 Kelvin, colder than the temperature of outer space. The protons are accelerated by electric fields arranged around the ring, gaining energy with each pass. After thousands of circuits, they reach their maximum velocity and are directed into collision at 4 intersection points around the ring, where the collisions are recorded by massive detector systems surrounding each collision point. The maximum energy achieved by protons in the Large Hadron Collider is approximately 6.5 TeV per proton, meaning 6.5 trillion electron volts. To reach this energy, each proton must be accelerated from its rest mass energy of approximately 938 million electron volts to 6.5 trillion electron volts. The ratio of kinetic plus rest mass energy to rest mass energy is the Lorentz factor, which means protons at maximum energy in the collider have a Lorentz factor of approximately 6,930. They are moving at approximately 99.9999991% of the speed of light, with the remaining gap to light speed being approximately 0.0000009%. The energy required to accelerate these protons is enormous by the standards of everyday experience. The collider consumes approximately 200 megawatts of electrical power during operation, comparable to the electricity consumption of a small city. But what is remarkable is not the absolute energy used, but the relationship between energy input and velocity achieved. The first 90% of light speed required a certain amount of energy. The next 9% required significantly more. The next 0.9% required even more. The next 0.09% more still. Each increment of velocity closer to light speed requires exponentially more energy than the previous increment, exactly as the Lorentz factor formula predicts. The protons at maximum energy in the collider are moving so fast that from their perspective, the entire 27-kilometer circumference of the ring is length contracted to approximately 3.9 meters. From the proton's reference frame, they are traveling around a tiny loop, not a 27-kilometer tunnel. And yet from the laboratory frame, they are traversing 27 kilometers more than 11,000 times per second. Both descriptions are correct, in their respective reference frames consistent with special relativity. When these protons collide, the consequences are spectacular in a very specific and informative way. The collision energy is so enormous that it can materialize as new particles according to Einstein's mass-energy equivalence. The total kinetic energy of the colliding protons, when concentrated into the tiny volume of a proton-proton collision, is sufficient to create particles far more massive than the protons themselves. Higgs bosons, which were first observed at the Large Hadron Collider in 2012, have a mass approximately 133 times the proton mass. They are created from the kinetic energy of protons moving at 99.9999991% light speed, and their existence and properties have been measured with considerable precision. Every property of these collisions that the detectors measure, every particle produced, every angle of scattering, every momentum distribution, every decay chain is consistent with special relativity to within experimental precision. Scientists have now performed trillions of proton-proton collisions at the Large Hadron Collider and at its predecessors, including the Tevatron at Fermilab and the Large Electron-Positron Collider that occupied the same tunnel before the LHC. Not one collision has ever produced a result inconsistent with special relativity. Not one particle has ever been observed to travel faster than light in any of these experiments. The theory is tested to a precision that exceeds virtually every other physical theory ever constructed. The collider also demonstrates directly what happens as you try to push a particle ever closer to light speed. The magnets that keep the protons on their circular path must exert a force calibrated to the relativistic momentum of the protons, not their classical momentum. At the energies involved, the relativistic momentum is nearly 7,000 times the classical momentum. If the magnets were designed using classical formulas, they would be completely inadequate. The fact that protons remain on track at 99.9999991% light speed is direct evidence that the magnets are compensating for the relativistic momentum enhancement, which is direct evidence that relativistic momentum enhancement is real and quantitatively matches the Lorentz factor formula. Time does not flow, it bends. The most counterintuitive prediction of special relativity is not the speed limit itself. It is what happens to time as you approach it. Time dilation, the slowing of clocks in motion, is not an analogy or a metaphor or a way of speaking loosely about measurement artifacts. It is a literal, physical, measurable phenomenon in which the passage of time genuinely runs at different rates for objects in different states of motion. The experimental confirmation of this fact is extensive and comes from multiple independent lines of evidence. The earliest direct experimental confirmation was the Hafele-Keating experiment of 1971, in which cesium atomic clocks were flown on commercial aircraft around the world and compared with identical clocks that remained at the US Naval Observatory. The results showed that the flying clocks disagreed with the stationary clocks by amounts consistent with special relativistic time dilation from the aircraft velocity and general relativistic time dilation from the aircraft altitude. The disagreements were tiny, measured in nanoseconds, but they matched Einstein's predictions within experimental uncertainty. Time was genuinely running at different rates for the moving clocks. The explanation of why time dilation occurs at the level of the underlying physics of spacetime, rather than just the mathematical formula, requires returning to the concept of spacetime geometry. Two objects taking different paths through spacetime between the same pair of events will accumulate different amounts of proper time along their respective paths. Proper time is the time measured by a clock that travels with the object, experiencing the same spacetime trajectory as the object itself. The proper time accumulated along a world line is determined by the geometric length of that world line in spacetime, measured in units where the time dimension is weighted by the speed of light. A world line that remains spatially stationary, running purely along the time dimension, accumulates the maximum possible proper time between two fixed events. Any deviation of the world line into the spatial dimensions reduces the proper time accumulated, because the space-time geometry penalizes spatial motion by reducing the temporal component of the world line's geometric length. This is not an artifact of measurement or a consequence of signal travel times. It is the geometry of space-time, and it is as real as the geometry of ordinary space. The analogy with ordinary geometry is helpful. If you want to travel between two cities, the straight line path is the shortest distance. Any deviation from the straight line, any detour, makes the journey longer. In space-time, the analogous statement is reversed due to the sign convention in the space-time metric. The straight world line through space-time, corresponding to a stationary object, is the path of maximum proper time, and any deviation into spatial motion reduces the proper time accumulated. Objects moving through space accumulate less proper time than stationary objects between the same pair of events, which is the geometric statement underlying time dilation. This reversal of the ordinary geometry intuition is one of the most conceptually challenging aspects of special relativity, but it has a clear physical interpretation. Moving through space consumes some of the four-dimensional space-time velocity budget that would otherwise go into moving through time. Less velocity directed into the time dimension means less time accumulated per unit of coordinate time. The clock runs slow because the object is spending some of its fixed space-time speed moving through space. The twin who came home 7 years younger. The twin paradox is the most famous thought experiment in special relativity, and it has been generating confusion and debate since Einstein's 1905 paper. Not because the physics is ambiguous, but because the situation seems to imply a contradiction that requires careful reasoning to resolve. The scenario is this: one twin stays on Earth while the other boards a spacecraft and travels to a distant star at near light speed, then returns. When the returning twin steps off the spacecraft, they are younger than their sibling who remained on Earth. Not slightly younger in a way requiring atomic clocks to detect, dramatically younger by years or decades depending on the velocity of travel. The time dilation experienced during the journey was real, physical, and permanent. The apparent paradox arises from the principle of relativity, which states that motion is relative and that there is no absolute rest frame. If the travelling twin is moving relative to the Earth is equally moving relative to the travelling twin. From the travelling twin's perspective, the Earth is the thing moving away at near light speed and then returning. Shouldn't the Earth-bound twin be the younger one from this perspective? And if both perspectives are valid, how can there be a definite answer about who is younger when they reunite? The resolution is that the situation is not symmetric, despite appearing to be so. The principle of relativity applies to inertial reference frames, meaning frames that are not accelerating. An inertial observer is one moving at constant velocity without turning or changing speed. The Earth-bound twin, to a good approximation ignoring Earth's rotation and orbital motion, remains in an inertial frame throughout the experiment. The travelling twin does not. To travel to a distant star and return, the travelling twin must accelerate away from Earth, decelerate at the destination, turn around, accelerate toward Earth, and decelerate to a stop upon arrival. These acceleration phases break the symmetry. The travelling twin is not in an inertial frame during these phases, and the principle of relativity does not guarantee equivalent perspectives for non-inertial observers. When the acceleration phases are properly accounted for using the mathematics of special relativity, the asymmetry resolves cleanly. The travelling twin accumulates less proper time than the Earth-bound twin, because their world line through space-time is longer in the spatial dimensions and correspondingly shorter in the temporal dimension. The Earth-bound twin ages more during the journey. When the twins reunite, the age difference is real and permanent. The travelling twin is younger by an amount that can be calculated precisely from the velocity and duration of travel. This is not a theoretical prediction awaiting confirmation. It has been confirmed experimentally in analogous scenarios. Subatomic particles called muons, produced in the upper atmosphere by cosmic ray collisions, have been studied extensively. Muons are unstable and decay with a characteristic half-life of approximately 2.2 microseconds when at rest. At the velocities at which cosmic ray muons travel, approximately 99.5% of the speed of light, the Lorentz factor is approximately 10. From the laboratory frame, the muons clocks run 10 times slower than a stationary muons clock, meaning they survive 10 times as long before decaying. This allows them to travel approximately 10 times farther before half of them have decayed, which is why muons created 10 to 15 kilometers high in the atmosphere survive long enough to be detected at ground level. Without time dilation, the muon flux at ground level would be orders of magnitude lower than observed. From the muon's perspective, the phenomenon is described differently, but with the same physical result. Rather than the muon's clock running slowly, the distance to Earth's surface is length contracted by the Lorentz factor of 10. Instead of needing to travel 12 kilometers in its 2.2 microsecond lifetime, the muon only needs to travel approximately 1.2 kilometers in a length contracted world. The two descriptions, time dilation in the laboratory frame and length contraction in the muon frame, are different perspectives on the same spacetime geometry. Both give the same measurable prediction for the muon flux at ground level, and both are confirmed by experiment. The twin paradox is thus not a paradox in the sense of a genuine contradiction. It is a puzzle that requires understanding the asymmetry between inertial and non-inertial reference frames. When that asymmetry is understood, the physics is completely consistent and completely confirmed by experiment. The twin who travels genuinely comes home younger, not by the kind of tiny fraction detectable only with atomic clocks, as in the Half-LA Keating experiment, but by years or decades in the scenario of interstellar travel at relativistic velocities. Time dilation is not a measurement quirk. It is the universe's geometry, applied to the biology of living organisms just as rigorously as it is applied to the oscillations of cesium atoms. The satellites proving Einstein right 24 hours a day. The global positioning system consists of at least 24 operational satellites orbiting Earth at an altitude of approximately 20,200 kilometers, each carrying a set of atomic clocks synchronized to within a few nanoseconds of each other and of ground-based reference clocks. The system works by having each satellite broadcast a signal containing the satellite's current position and the exact time the signal was transmitted. A GPS receiver on the ground receives signals from multiple satellites simultaneously and calculates the distance to each satellite from the travel time of the signal, multiplying by the speed of light. With distances from 4 or more satellites, the receiver can calculate its three-dimensional position and the current time with remarkable precision. The precision of the system depends critically on the timing accuracy of the satellite clocks. Light travels approximately 30 centimeters in 1 nanosecond. A clock error of just 1 nanosecond introduces a positioning error of approximately 30 centimeters. A clock error of 1 microsecond introduces an error of approximately 300 meters. For navigation to be useful at the level of tens of meters or better, the satellite clocks must be accurate to tens of nanoseconds or better. Here is the problem that Einstein creates for GPS engineers. The satellite clocks are not stationary relative to Earth's surface. They orbit at approximately 3.87 kilometers per second, which is not remotely close to the speed of light, but is fast enough to produce a measurable special relativistic time dilation effect. At this velocity, special relativity predicts that the satellite clocks should run slow relative to ground clocks by approximately 7.2 microseconds per day. Left uncorrected, this would cause a positioning error of approximately 2.16 kilometers per day, accumulating without bound. But this is not the only relativistic effect at work. General relativity, Einstein's theory of gravity, predicts that clocks run faster in weaker gravitational fields. At an altitude of 20,200 kilometers, the gravitational field of Earth is significantly weaker than at Earth's surface. General relativity predicts that this should cause satellite clocks to run fast relative to ground clocks by approximately 45.9 microseconds per day. The gravitational effect dominates over the velocity effect, and the net result is that GPS satellite clocks run fast relative to ground clocks by approximately 38.7 microseconds per day. An error of 38.7 microseconds per day corresponds to a positioning error of approximately 11.6 kilometers per day. Without any correction, GPS would be useless for precision navigation within hours of operation. The system would drift from useful precision to kilometre-scale errors within the first day, and to tens of kilometres errors within a week. The GPS designers knew this. They built the relativistic correction into the system from the beginning. Each satellite's clocks are set to run at a slightly lower frequency before launch, by exactly the amount predicted by combining special and general relativistic effects, so that when the satellite reaches orbit and the relativistic effects take hold, the clocks run at exactly the correct rate. The clocks are also regularly monitored and corrected for any remaining discrepancies. The correction value was calculated using Einstein's equations and implemented in hardware before the system was deployed. The system works. GPS navigation is accurate to meters. This is not because the relativistic correction is approximate and the system is somehow robust to the error. The correction is precise and necessary. Every GPS navigation calculation that gives you a correct position is simultaneously confirming that special and general relativity are correct to the precision required for the calculation to succeed. Billions of GPS position calculations are performed every day around the world, in cars and airplanes and ships, and surveying equipment and mobile phones. Every successful calculation is a confirmation of Einstein's equations. Every meter of positioning accuracy is a measurement of relativistic time dilation working exactly as predicted. The particles falling from the sky that should not exist. Every second, approximately 10,000 muons pass through every square meter of Earth's surface at sea level. Muons are unstable subatomic particles produced when cosmic rays, primarily high-energy protons from sources throughout the galaxy and beyond, collide with nitrogen and oxygen nuclei in the upper atmosphere at altitudes of approximately 10 to 15 kilometers. These collisions produce pions, which quickly decay into muons. The muons then travel downward through the atmosphere at velocities very close to the speed of light. Here is the problem. Muons are unstable. They decay into electrons and neutrinos with a characteristic half-life of approximately 2.197 microseconds. This means that starting from a population of muons, half of them will have decayed after 2.197 microseconds, 3/4 after 2 half-lives, 4.394 microseconds, and so on. The half-life is a fixed property of the muon that can be measured precisely in laboratory experiments with muons at rest. Now consider the travel time. The muons are produced at approximately 10 to 15 kilometers altitude and must travel to sea level, a distance of 10,000 to 15,000 meters. They travel at approximately 99.5% of the speed of light, which is approximately 298 million meters per second. The travel time from production to sea level is therefore approximately 10,000 divided by 298 million, which is approximately 33 microseconds. The half-life of a muon at rest is 2.197 microseconds. In 33 microseconds, approximately 15 half-lives would elapse. After 15 half-lives, the fraction of the original population remaining is 2 to the power of -15, which is approximately 1 in 32,768. Starting from the number of muons produced at altitude, only about 1 in 32,768 should survive to sea level. The muon flux at sea level should be minuscule, far too low to detect without extremely sensitive equipment, but detectors at sea level count approximately 10,000 muons per square metre per second. The muons are there in large numbers, far more than classical physics would predict. They are surviving a journey that their half-life should prevent them from making. This is not a statistical fluctuation or a measurement artifact. It has been confirmed repeatedly in experiments at different altitudes and with different detector configurations. The muon flux at sea level is dramatically higher than classical physics predicts. The explanation is time dilation. From the laboratory frame, the muons are moving at 99.5% of the speed of light, giving them a Lorentz factor of approximately 10.0. Their clocks run 10 times more slowly than laboratory clocks. In laboratory time, it takes 33 microseconds for the muons to travel from production altitude to sea level. But in muon proper time, which is what governs the decay rate, only 33 divided by 10, which is 3.3 microseconds, elapse during the journey. In 3.3 microseconds, only about 1.5 half-lives pass. The fraction of muons surviving is 2 to the power of -1.5, approximately 35%. The muon flux at sea level is approximately 35% of the flux at production altitude. This matches what detectors observe. From the muon's reference frame, the explanation involves length contraction rather than time dilation, but the physical prediction is identical. In the muon's frame, the atmosphere is length contracted by the Lorentz factor of 10. Instead of being 10,000 to 15,000 meters thick, the atmosphere appears only 1,000 to 1,500 meters thick. The muons travel this contracted distance in approximately 3.3 microseconds of proper time, again consistent with 35% survival. Both reference frames give the same observable result because they are both describing the same spacetime geometry. The muon observation is particularly compelling as evidence for time dilation because it involves no instruments, no synchronization procedures, no calibration uncertainties. It is a directly observable fact about the natural world. Muons created at altitude survive to reach sea level in numbers that are explicable only by time dilation. Remove time dilation from the calculation and the prediction fails dramatically. Include it and the prediction matches observation precisely. The particles falling from the sky that should not exist are the universe's own demonstration that Einstein was right. What happens to space itself at extreme velocity? Time dilation is the relativistic effect that most people encounter first because it involves time, which is something everyone has an intuitive relationship with. Clocks running slow, twins aging at different rates, particles living longer than they should. These are phenomena that can be described in everyday language, even if the underlying physics is strange. The companion effect, length contraction, is equally real and equally well confirmed, but it is somewhat harder to develop intuition for because it involves space rather than time. And our intuitions about space are even more deeply rooted than our intuitions about time. Length contraction is the phenomenon by which objects moving at high velocity are physically shorter in the direction of their motion, as measured by observers who are stationary relative to the object. The contraction is not an optical illusion caused by the finite travel time of light from different parts of the object. It is not a measurement artifact arising from the synchronization of clocks. It is a genuine geometric property of the object's world line through spacetime, as real as the time dilation that accompanies it. The two effects are not independent phenomena that happen to coexist. They are two aspects of a single underlying reality, the geometry of spacetime and the way different world lines through that geometry relate to the dimensions of space and time. The formula for length contraction involves the same Lorentz factor that governs time dilation. An object at rest has a proper length, the length measured in its own rest frame. An observer measuring the length of the same object while it is moving will measure a contracted length equal to the proper length divided by the Lorentz factor. At low velocities, the Lorentz factor is very close to 1, and the contraction is undetectable. As velocity approaches light speed, the Lorentz factor grows without bound, and the measured length approaches 0. At 10% of light speed, the Lorentz factor is approximately 1.005, and the contraction is 5 parts in 1,000. A 10-meter object appears 9.95 meters long. At 50% of light speed, the Lorentz factor is approximately 1.155, and the object appears 8.66 meters long. At 90%, the Lorentz factor is approximately 2.29, and the object appears 4.37 meters long, less than half its rest length. At 99%, the Lorentz factor is approximately 7.09, and the object appears 1.41 meters long, about 14% of its rest length. At 99.9%, the Lorentz factor is approximately 22.4, and the object appears just 0.45 meters long. A 10-meter spacecraft compressed to less than half a meter, as measured from the stationary frame. The directionality of the contraction is important. Length contraction acts only along the direction of motion. An object moving in the forward direction is contracted in the forward direction. Its dimensions perpendicular to the motion, its height and width, if it is moving forward, are not affected. This asymmetry is a direct consequence of the space-time geometry. The space-time metric mixes the time dimension with the spatial dimension along the direction of motion, but leaves the perpendicular spatial dimensions unchanged. So the effects of relative motion are anisotropic. They act on the component of space aligned with the velocity. From the moving object's own reference frame, the contraction looks different. The object does not appear contracted to observers inside it. Their own measurements of the object's dimensions give the full rest length. What appears contracted to them is the external world, specifically the distances ahead of and behind them in their direction of travel. If a spacecraft is traveling at 99% of light speed toward a star 100 light-years away, observers on Earth measure the star as 100 light-years distant. Observers on the spacecraft measure the same star as approximately 14 light-years away, because the distance is contracted by the Lorentz factor of approximately 7.09. From the spacecraft's frame, the journey is 14 light-years, not 100. This has a remarkable practical implication. An astronaut travelling at 99% of light speed toward a star 100 light-years away would experience the journey taking approximately 14 light-years divided by 99% of light speed, which is approximately 14.1 years of proper time. They would age about 14 years during the trip. From Earth's perspective, the journey takes approximately 101 years. The astronaut arrives at the star 101 years after departing Earth, but has only aged 14 years during the transit. Both descriptions are correct and consistent. The Earth frame description uses time dilation. 101 years pass on Earth, while only 14 pass for the astronaut. The astronaut frame description uses length contraction. The distance to the star is only 14 light-years, so at 99% light speed, the journey takes about 14 years. The experimental confirmation of length contraction is embedded in the same muon physics discussed in the previous chapter, but the description is from the muon's reference frame rather than the laboratory frame. From the muon's perspective, it is at rest, and the atmosphere is rushing toward it at 99.5% of the speed of light. The atmosphere's thickness is length contracted by the Lorentz factor of approximately 10. Instead of being 10 to 15 kilometers thick, the atmosphere appears only 1 to 1.5 kilometers thick. The muon travels this contracted distance in approximately 3.3 microseconds of proper time, comfortably within its 2.197 microsecond half-life for a substantial fraction to survive. The two reference frame descriptions, time dilation from Earth's frame and length contraction from the muon's frame, give identical physical predictions for the muon's survival fraction at ground level. At the speed of light, length contraction becomes complete in the direction of motion. A photon, moving at exactly the speed of light with the Lorentz factor undefined for massive objects, but with the contraction formula suggesting complete collapse for massless particles, does not experience any spatial extent in its direction of travel. The distance between any 2 points along its path is zero from its perspective, in the sense that massless particles have no well-defined rest frame. The beginning and end of any photon's journey are separated by zero spacetime interval in the null geodesic sense. The event of emission and the event of absorption are connected by a path of zero spacetime length, despite potentially being separated by billions of light years in both space and ordinary time from the laboratory frame. Why faster than light travel destroys causality itself. The connection between the speed of light and the logical structure of cause and effect is deeper than a mere correlation or a coincidental numerical agreement. The speed of light is the causal speed of the universe, the rate at which cause becomes effect across a spatial separation. Any signal travelling faster than light would, in at least some reference frames, arrive before it was sent. Effects would precede causes. The logical structure of reality, the requirement that an event cannot be influenced by something that has not yet happened, would be violated. This is not an aesthetic objection. It is a fundamental requirement for any coherent description of physics. To see why faster than light travel implies backward causation, consider two events. Event A, the sending of a faster than light signal, and Event B, the receipt of that signal. In the reference frame of the sender, B occurs after A. The signal was sent at a certain time and received at a later time, travelling faster than light across some spatial distance. Now consider a different reference frame, one moving with a velocity relative to the sender in the same direction as the signal, but at a speed below the speed of light. In special relativity, the relative timing of spatially separated events is reference frame dependent for events with a space-like separation. Two events have a space-like separation if no signal travelling at or below light speed could travel between them, which means they cannot be causally connected in the normal sense. The faster-than-light signal connects events A and B with precisely this kind of space-like separation. In the sender's frame, B is later than A, but in a reference frame moving in the appropriate direction at an appropriate speed, the ordering of A and B is reversed. B occurs before A. The signal arrives before it is sent. In another reference frame, A and B are simultaneous. The order of cause and effect is not absolute. It depends on which reference frame you occupy. This might seem like merely a philosophical curiosity if faster-than-light travel were only possible in one specific reference frame. But special relativity tells us that if faster-than-light travel is possible in any inertial reference frame, it must be possible in all inertial reference frames, because the laws of physics are the same in all inertial frames. If an alien civilization can send faster-than-light signals in their reference frame, then we can send faster-than-light signals in our reference frame. And the combination of two faster-than-light signals, one sent from Earth to a moving spacecraft and one sent back from the spacecraft to Earth, can result in a reply arriving before the original message was sent. The construction of a causal paradox from faster-than-light communication follows a specific logical chain. Suppose a faster-than-light communicator can send a message that arrives at its destination before it was sent, by some interval of time in some reference frame. An experimenter sends a message to a receiving station. Upon receiving the message, the station immediately sends a reply back using the same faster-than-light technology. Under the appropriate conditions of relative motion and signal speeds, the reply can arrive at the original sender before the original message was transmitted. The sender receives a reply to a message they have not yet sent. This creates a logical problem even before considering whether the sender could use the information to prevent sending the original message, which would be the classic causal loop. Even without the self-defeating aspect, receiving information from the future creates contradictions with our understanding of how knowledge is acquired and how decisions are made. If you know the outcome of a coin flip before the coin is tossed, the outcome is determined before the event occurs, which is inconsistent with the fundamental randomness of quantum mechanics. Faster-than-light communication and quantum randomness cannot both be correct. The universe appears to protect its causal structure actively. Quantum mechanics, which governs the behavior of particles at the smaller scales, contains a feature that makes faster-than-light information transfer impossible, even in situations that superficially appear to permit it. Quantum entanglement is a phenomenon in which two particles are prepared in a correlated state, such that measuring one particle instantly affects the state of the other, regardless of the distance between them. This correlation is real, measurable, and occurs instantaneously across any distance. It does not diminish with distance. It has been confirmed in experiments with entangled particles separated by hundreds of kilometers. At first glance, this seems to be exactly the faster-than-light influence that special relativity forbids. But the crucial distinction is between an influence and the transmission of information. Although measuring one entangled particle instantly affects the other's state, the measurement outcome at each particle is individually random. A measuring device at one end sees a random result. A measuring device at the other end sees a different random result. The two results are correlated, but neither party can choose what result they observe. An experimenter cannot encode a message in an entangled particle's measurement result because the result is not under their control. To discover the correlation, the two parties must compare their results using a conventional, slower-than-light communication channel. The entanglement does not permit faster-than-light information transfer. It permits only faster-than-light correlation, which has no causal effect and carries no information. The causal structure of the universe is therefore protected at multiple levels. Special relativity makes faster-than-light travel imply backward causation in some reference frames. Quantum mechanics makes faster-than-light information transfer impossible even through entanglement. These two protections appear to be related at a fundamental level through the requirements of relativistic quantum field theory, though the exact relationship is an active area of theoretical research. The universe is not merely enforcing the speed limit through the practical difficulty of achieving it. It is enforcing it through the logical requirements of causality itself. The rocket equation and the fuel problem that has no solution. The energy required to accelerate a massive object to near light speed is enormous, as the previous chapters established. But the energy alone does not capture the full severity of the situation. The energy must come from somewhere, and for any spacecraft that carries its own fuel, the Tsiolkovsky rocket equation governs the relationship between the fuel mass, the payload mass, the exhaust velocity, and the final velocity achieved. This equation creates a problem that compounds on top of the energy problem, making relativistic travel not merely energy intensive, but practically impossible by any foreseeable means. The Tsiolkovsky rocket equation, derived in 1897 by the Russian mathematician Konstantin Tsiolkovsky, relates the change in velocity achievable by a rocket to the exhaust velocity of its propellant and the ratio of its initial mass, including fuel, to its final mass, payload plus empty vehicle. The key insight of the equation is that the fuel required grows exponentially with the velocity change desired. To achieve a velocity change equal to the exhaust velocity, the initial mass must be approximately 2.72 times the final mass, nearly 3 kilograms of fuel per kilogram of payload. To achieve twice the exhaust velocity, the initial mass must be approximately 7.39 times the final mass. 3 times the exhaust velocity requires approximately 20 times the mass. The required fuel-to-payload ratio grows as the mathematical constant e raised to the power of the velocity ratio. And this exponential growth creates problems that rapidly become unsurmountable. For chemical rockets, the maximum exhaust velocity is determined by the energy released in chemical combustion and the molecular weight of the combustion products. The best chemical propellants achieve exhaust velocities of approximately 4.5 kilometers per second. The speed of light is approximately 300,000 kilometers per second. To reach even 1% of the speed of light, approximately 3,000 kilometers per second, using a chemical rocket would require a mass ratio of e to the power of 3,000 divided by 4.5, which is e to the power of approximately 667. The number e to the 667th power is so astronomically large that it exceeds the number of atoms in the observable universe by an incomprehensible factor. Chemical propulsion for relativistic velocities is not merely impractical. It is more impossible than the concept of impossibility typically conveys. Ion drives, which use electric fields to accelerate ions to high velocities and achieve much higher exhaust velocities than chemical rockets, do considerably better. The best current ion drives achieve exhaust velocities of approximately 30 to 90 kilometers per second. To reach 1% of light speed using an ion drive with 90 kilometers per second, exhaust velocity would require a mass ratio of e to the power of approximately 33, which is approximately 214 billion kilograms of propellant per kilogram of payload. A spacecraft with a 1-ton payload would need approximately 214 billion tons of propellant. The entire mass of Earth is approximately 6 trillion metric tons, so the propellant for a relativistic ion drive mission would require processing a mass comparable to a very large asteroid just to carry 1 metric ton of payload to 1% of light speed. Nuclear fission rockets, which use the energy released by fissioning heavy elements to heat and expel a propellant, can achieve exhaust velocities of approximately 10,000 meters per second. About 10 times better than chemical rockets, but still leaving enormous mass ratios for relativistic velocities. Nuclear fusion rockets, if they could be made to work, could in principle achieve exhaust velocities of several percent of the speed of light, dramatically improving the situation. A fusion rocket with an exhaust velocity of 10% of light speed, targeting a final velocity of 50% of light speed, would require a mass ratio of e to the power of 5, approximately 148 kilograms of fuel per kilogram of payload. Challenging, but not obviously absurd. At 90% of light speed, the same rocket requires e to the power of approximately 14.7, or approximately 2.4 million kilograms of fuel per kilogram of payload. At 99%, e to the power of approximately 21.7, or approximately 2.7 billion kilograms of fuel per kilogram of payload. The numbers are getting back to absurd, even for fusion. And fusion rockets do not yet exist. Humanity has been attempting to achieve controlled nuclear fusion for more than 60 years. As of the current state of the art, no fusion reactor has sustained net energy output. Fusion-powered propulsion is a technology that, even if every optimistic projection comes true, lies decades in the future. Using it for relativistic propulsion lies much further. The situation is further complicated by the relativistic generalization of the rocket equation, which accounts for the fact that at high velocities, the relationship between momentum change and velocity change is governed by the Lorentz factor. The relativistic rocket equation gives even worse fuel requirements than the classical version at high velocities. For a spacecraft targeting 90% of light speed using antimatter annihilation as propellant, with an exhaust velocity equal to the speed of light, the theoretical maximum for any propulsion system, the required mass ratio is approximately 6.6 kilograms of fuel per kilogram of final mass. This is actually achievable in principle if antimatter could be produced and stored in these quantities. For a round trip to a destination at 90% of light speed, including deceleration at the destination and acceleration and deceleration for the return, the required mass ratio becomes approximately 43 kilograms of fuel per kilogram of payload. A 1-ton spacecraft requires 43 tons of antimatter fuel. The problem is that antimatter does not exist in nature in macroscopic quantities and can only be produced artificially in particle accelerators at extraordinary energy cost. The total amount of antimatter produced by all of humanity's particle accelerators throughout the entire history of accelerator physics is approximately 20 nanograms, 20 billionths of 1 gram. The fuel requirement for a relativistic antimatter rocket mission, even optimistically at 90% of light speed, is tens of tons. The gap between what has been produced and what is needed is a factor of approximately 10 to the 18th power, 1 quintillion times more than has ever been made. The perfect fuel that still is not enough. Antimatter is the most energy-dense fuel that physics permits. When a particle of matter meets its antimatter counterpart, both annihilate completely, and all of their combined mass is converted to energy, according to Einstein's equation. The efficiency is 100%. Every atom of fuel contributes to the energy output. No chemical reaction approaches this. No nuclear fission or fusion reaction approaches it. Fission converts about 0.1% of mass to energy. Fusion converts about 0.3 to 0.7%. Matter-antimatter annihilation converts 100%. It is the absolute thermodynamic ceiling for energy density in any fuel that can be stored and carried on a spacecraft. 1 kilogram of matter combined with 1 kilogram of antimatter releases approximately 1.8 times 10 to the 17th joules of energy. This is approximately 43 megatons of TNT, equivalent from 2 kilograms of fuel. For comparison, 1 kilogram of the most energetic chemical explosive releases approximately 4 to 6 megajoules, roughly 1 to 2 kilograms of TNT equivalent. Antimatter is approximately 43 billion times more energy dense than chemical explosives. The gap between antimatter and any chemical fuel is so vast that it makes chemical fuels irrelevant for any calculation involving relativistic propulsion. Even with this extraordinary energy density, the fuel requirements for relativistic travel are severe. The problem is that reaching high percentages of the speed of light requires enormous kinetic energies, and even converting matter to energy at 100% efficiency requires substantial amounts of matter to do the converting. A spacecraft of 1,000 kilograms targeting 99% of light speed needs, as calculated from the relativistic rocket equation with antimatter propellant, approximately 14 kilograms of antimatter per kilogram of payload for a one-way trip. For the spacecraft itself of 1,000 kilograms, that means approximately 14,000 kilograms, or 14 metric tons, of antimatter just to accelerate to 99% of light speed. For a round trip including deceleration at the destination and the return journey with its own acceleration and deceleration, the mass ratio compounds to approximately 200 kilograms of antimatter per kilogram of payload, meaning 200 metric tons of antimatter for a 1,000 kilogram spacecraft. The fuel outweighs the spacecraft by a factor of 200, and this assumes perfect efficiency in converting the annihilation energy into directed thrust, which is itself a significant unsolved engineering problem. Antimatter annihilation primarily produces high-energy gamma rays and pions. Gamma rays cannot be directed by any magnetic nozzle. Converting them into directed thrust requires a series of energy conversion steps, each with its own efficiency loss. Realistic antimatter propulsion systems might achieve exhaust velocities of 70 to 90% of light speed, with efficiencies that further multiply the required fuel mass. The production problem dwarfs even the engineering challenges. Creating antimatter requires accelerating particles to high energies and colliding them with targets, producing particle-antiparticle pairs from the collision energy. The process is inherently inefficient. Far more energy goes into the collision than is stored in the created antimatter, because most of the collision energy goes into creating both the particle and the antiparticle, and the particle immediately annihilates with normal matter, while the antiparticle must be extracted and stored before it does the same. The overall energy efficiency of antimatter production at CERN is approximately 10 to the minus 9. 1/billionth of the input energy ends up stored in antimatter. Every joule of antimatter costs 1 billion joules of electricity to produce. This means that even if the engineering challenges of antimatter rockets were completely solved, the energy cost of producing the antimatter fuel for a relativistic mission would be many times greater than the kinetic energy the mission achieves. You would be taking energy from a power source, converting it to electricity, using the electricity to produce antimatter at 0.0000001% efficiency, storing the antimatter, and then releasing it on the spacecraft to provide thrust. The net result is a scheme that is many millions of times less efficient than simply beaming the original energy directly to the spacecraft as electromagnetic radiation. Antimatter propulsion, for all its theoretical attractiveness as the most energy-dense fuel possible, is a dramatically inefficient way to store and release energy. The storage problem is equally prohibitive. Antimatter cannot be stored in any ordinary container because it annihilates on contact with normal matter. It must be suspended in vacuum using magnetic or electric fields that prevent it from touching the container walls. The largest antimatter storage system ever built at CERN uses a combination of magnetic and electric fields to suspend approximately 10 to the 6 antiprotons for periods of up to 15 minutes. Scaling this to tons of antimatter for a spacecraft mission would require storage systems orders of magnitude beyond anything currently conceivable, operating continuously for the years or decades of a relativistic voyage without any failure, because a single failure of the containment would result in the instantaneous detonation of the stored antimatter with explosive yield measured in tens or hundreds of megatons. The conclusion from the fuel analysis is the same as the conclusion from the energy analysis, approached from a different direction. The perfect fuel, the one that extracts every possible joule from every gram of propellant, is not adequate for practical relativistic travel. It is barely adequate in theory for 99% light speed on a one-way trip, and it is inadequate by factors of trillions in terms of what we can actually produce. The fuel problem is not an engineering challenge that will be solved by better chemistry or better engineering. It is a reflection of the fundamental thermodynamics of the universe, and the fundamental thermodynamics of the universe makes carrying fuel for relativistic travel essentially impossible at any scale relevant to human missions. The dust grain that hits like a nuclear weapon. Suppose, for the sake of argument, that all previous problems were solved. Suppose that some future technology achieved the energy required for relativistic travel, solved the fuel-mass ratio problem, produced and stored the necessary antimatter, and successfully accelerated a spacecraft to 90% or 99% of the speed of light. There would still be a problem that has no obvious solution, and that, in the opinion of many physicists, may be the most practically severe obstacle to relativistic travel. The interstellar medium is not empty, and at relativistic velocities, the particles in it become catastrophically energetic. The interstellar medium contains approximately 1 hydrogen atom per cubic centimetre on average, though with significant variation from region to region. This is an extraordinarily low density by terrestrial standards. Earth's atmosphere at sea level contains approximately 2.7 times 10 to the 19th molecules per cubic centimetre, roughly 27 quintillion times denser. The interstellar medium is the best natural vacuum in the accessible universe, far better than any vacuum achievable in terrestrial laboratories. At ordinary spacecraft velocities, the effect of hitting these sparse atoms is completely negligible. Voyager 1, travelling at approximately 17 kilometres per second, encounters perhaps a few 100,000 atoms per second across its frontal area, and these collisions have no measurable effect on the spacecraft. The situation changes completely at relativistic velocities. Kinetic energy scales as 1/2 times mass times velocity squared at low velocities, but the relativistic formula for kinetic energy is the Lorentz factor -1 times the rest mass energy. At 99% of light speed, the Lorentz factor is approximately 7.09, meaning each collision carries approximately 6.09 times the rest mass energy of the impacting particle in kinetic energy. For a hydrogen atom with a rest mass of approximately 1.67 times 10 to the -27th kilograms, the kinetic energy in the spacecraft's reference frame is approximately 6.09 times 1.67 times 10 to the -27th times the speed of light squared, which is approximately 9.2 times 10 to the -10 joules per atom. One atom carries nearly 1 nanojoule of kinetic energy. That still sounds small, but now consider the rate at which atoms are encountered. A spacecraft with a frontal cross-section of 10 square meters traveling at 99% of light speed sweeps through a volume of 10 square meters times the spacecraft's velocity, approximately 2.97 times 10 to the 8th meters per second. The number of atoms encountered per second is this volume sweep rate times the number density of 1 atom per cubic centimetre, which is 10 to the 6th atoms per cubic metre. The rate is 10 square metres times 2.97 times 10 to the 8th metres per second times 10 to the 6th atoms per cubic metre, equaling approximately 2.97 times 10 to the 15 atoms per second. About 3 quadrillion atoms per second hitting the frontal surface of the spacecraft. Each atom carries approximately 9.2 times 10 to the -10 joules. 3 quadrillion of them per second deliver approximately 2.97 times 10 to the 15 times 9.2 times 10 to the -10 joules per second, which equals approximately 2.7 million watts of power deposited into the spacecraft's frontal surface. 2.7 megawatts of radiation bombardment from hydrogen atoms alone, continuously throughout the entire voyage. This is in addition to the galactic cosmic rays, which the Voyager spacecraft measured and which are already present in the interstellar medium at levels approximately twice those in the inner solar system. A relativistic spacecraft would experience an artificial cosmic ray environment from the hydrogen atoms it is slamming into at 99% of light speed, each one arriving with energies in the millions of electron-volt range, characteristic of energetic cosmic rays. The radiation damage this would cause to any material known is severe. Crystalline materials, including metals and semiconductors, suffer radiation damage from energetic particle bombardment through a process called displacement damage. Each impacting particle knocks atoms out of their lattice positions, creating defects that degrade the material's mechanical and electronic properties. Sufficient displacement damage embrittles metals, causes electronic components to malfunction, and eventually causes materials to lose structural integrity. The dose of displacement damage equivalent delivered to the spacecraft's frontal material at 99% light speed would be comparable to being inside an operating nuclear reactor, continuously for the entire duration of the voyage. Now consider larger particles. The interstellar medium also contains dust grains, particles of silicate minerals, and carbonaceous compounds ranging in size from a few nanometers to perhaps a micrometer. Their number density is approximately 10 to the minus 6 per cubic centimeter, 1,000,000 times less than hydrogen atoms, but their mass is enormously greater. A dust grain of 1 microgram mass, 10 to the minus 9 kilograms, hitting a spacecraft at 99% of light speed carries a kinetic energy of approximately 6.09 times 10 to the minus 9 times the speed of light squared, which is approximately 5.5 times 10 to the 8th joules, 550 megajoules. This is the energy equivalent of approximately 130 kilograms of TNT from a single microscopic dust grain smaller than a speck of visible dust. The explosion generated by this collision would be contained within the spacecraft's structure. The grain itself would vaporize instantly, producing a plasma jet that would penetrate deeply into any realistic shielding material. The energy deposition would be localized in a tiny volume near the impact point, creating shock waves that propagate through the spacecraft structure. A succession of such impacts over a voyage of even a few light years would be catastrophic for any known engineering material. Larger grains, millimeter scale or centimeter scale particles that exist in the interstellar medium at very low densities but are nonetheless present over the enormous path lengths of interstellar travel, carry energies that scale with mass. A 1 gram particle at 99% light speed carries approximately 5.5 times 10 to the 14th joules, more than 130,000 tons of TNT equivalent. This is equivalent to the yield of several dozen large nuclear weapons, all delivered to a single point on the spacecraft's hull in a fraction of a nanosecond. No engineering material and no conceivable shielding could survive such an impact. The spacecraft would be vaporized. Solutions to the particle impact problem have been proposed. Active particle deflection using powerful magnetic fields could deflect charged particles before they reach the spacecraft. But dust grains and neutral atoms are not deflected by magnetic fields. Particle beams projected forward to ionize approaching particles before they reach the spacecraft could in principle charge the particles enough for magnetic deflection to work. But the power required to ionize a cubic kilometre of interstellar space ahead of the spacecraft continuously throughout a voyage of several light years is absurd. A forward-facing ablative shield of sufficient thickness to survive the continuous bombardment would need to be replenished constantly and would itself require enormous mass to be carried. No proposed solution to the particle impact problem is convincing at 99% light speed over interstellar distances. The loopholes physics seems to allow and why they probably do not work. The obstacles to reaching or exceeding the speed of light within conventional spacetime have led some physicists to ask whether the structure of spacetime itself might allow shortcuts. If moving through spacetime is limited to the speed of light, perhaps one can manipulate spacetime, stretching and compressing it, to achieve effective faster-than-light travel without any local violation of the speed limit. Two principal candidates have been proposed: the Alcubierre warp drive, which involves contracting space ahead of a spacecraft and expanding it behind, and traversable wormholes, which connect two distant regions of spacetime through a tunnel of finite proper length. Both are mathematically consistent with general relativity's field equations. Both require physical conditions that may not be achievable in our universe. The Alcubierre drive was proposed by Mexican physicist Miguel Alcubierre in 1994 in a paper in the journal Classical and Quantum Gravity. Alcubierre found a solution to Einstein's field equations that describes a region of flat spacetime, the interior of the warp bubble, surrounded by a region of distorted spacetime in which space contracts ahead of the bubble and expands behind it. Inside the bubble, a spacecraft sits in flat spacetime and experiences no acceleration and no relativistic effects. From outside, the bubble moves at superluminal speeds by riding on the wave of contracting space ahead, much as a surfer rides on the crest of an ocean wave. The analogy is imprecise, but captures the essential idea. The spacecraft is not moving through space faster than light. Space itself is moving around the bubble, carrying the spacecraft along. This construction appears at first to be a genuine loophole. The spacecraft's velocity through the local spacetime of the bubble interior never exceeds the speed of light. No local violation of special relativity occurs. Yet the spacecraft can traverse vast distances in times that would require superluminal travel through flat spacetime, effectively moving faster than light from the perspective of distant observers. The problem is the energy required to create and maintain the warp bubble. Alcubierre's calculation of the stress-energy tensor, the quantity in general relativity that describes the distribution of mass energy that must be present to produce a given space-time geometry, showed that the warp bubble requires regions of negative energy density, not low positive energy density. Actual negative energy density below the 0-point vacuum energy of empty space. This is the same exotic matter discussed in the context of wormholes, and it may not exist in our universe in the required quantities. The magnitude of negative energy required is staggering. Alcubierre's original calculation indicated that a warp bubble with a 10-meter radius moving at 10 times the speed of light would require negative energy comparable to the total mass energy of a planet the size of Jupiter, but negative. Harold White at NASA's Johnson Space Center later proposed geometric modifications to the bubble shape that might reduce the required exotic energy by many orders of magnitude, and his team attempted to detect microscale warp field effects in laboratory experiments using interferometry. No confirmed detection was made. The energy requirements, even with White's optimizations, remained far beyond anything achievable with current or foreseeable technology. A deeper problem with the Alcubierre drive was identified by several physicists independently. It may be impossible to create or control from inside the bubble. To switch on the warp drive, a signal must be sent from inside the bubble to the region of spacetime that is being warped. But the region of spacetime being warped is precisely the region that a light signal from inside the bubble cannot reach, because the bubble's superluminal motion places those regions outside the light cone of the bubble's interior. The occupants of the bubble cannot turn it on or off or steer it. They are passengers with no control over their destination. The problem of how to initiate the warp bubble in the first place from an initial state of flat spacetime while respecting causality has not been resolved. Traversable wormholes, popularized by Kip Thorne and Michael Morris in a 1988 paper in the American Journal of Physics, are solutions to Einstein's field equations that connect two distant regions of spacetime through a tunnel. An object entering one mouth of the wormhole emerges from the other mouth, regardless of the distance between the mouths in ordinary space. If the two mouths are far apart, the wormhole provides a shortcut that effectively allows faster-than-light travel between the connected regions without any local superluminal motion. The same exotic matter requirement applies. To keep the wormhole open against its tendency to collapse, the throat must be threaded with matter of negative energy density. The required amount is less catastrophic than for the Alcubierre drive for small wormholes, but it is still enormous by comparison with anything producible by known physics. And wormholes have an additional problem. They are natural time machines. If one mouth of a wormhole is accelerated to high velocity relative to the other and then brought back, time dilation means the two mouths exist at different times. An object travelling through the wormhole from the slower age mouth to the faster age mouth travels backward in time. The possibility of closed time-like curves, paths through space-time that return to their own past, introduces the same causal paradoxes that faster-than-light travel creates, and the universe may protect against this through quantum effects that destabilize traversable wormholes before they can form. What quantum gravity might change about everything. General relativity and quantum mechanics are the two most successful physical theories in human history. General relativity describes the behavior of gravity, the large-scale structure of the universe, black holes, and gravitational waves. Quantum mechanics describes the behavior of matter and the three non-gravitational forces at the smaller scales. Both are confirmed to extraordinary precision by experiment. Both have no known failures in their domains of applicability. They are also fundamentally inconsistent with each other. The mathematics of quantum mechanics is built on a fixed background spacetime. The mathematics of general relativity treats spacetime as dynamic, curved by the presence of mass and energy. Combining the two requires describing a dynamic spacetime using quantum mechanics, which leads to mathematical infinities that cannot be removed by the renormalization techniques that tame infinities in quantum theories of the other forces. The unification of quantum mechanics and gravity into a single consistent theory is the central unsolved problem of theoretical physics, and it has been unsolved for nearly a century. What this means for the speed of light and the fundamental speed limit is uncertain, but potentially significant. The speed of light, as established by special relativity and confirmed by all experiments, is derived from the structure of classical spacetime, a continuous, smooth, four-dimensional manifold with the Lorentz metric. If spacetime is actually quantized at the smaller scales, as many quantum gravity candidates propose, the continuous smooth structure that gives rise to the classical speed limit may be an approximation valid at large scales, but breaking down at the Planck scale. The Planck length, approximately 1.616 times 10 to the minus 35 meters, and the Planck time, approximately 5.4 times 10 to the minus 44 seconds, define the scale at which quantum gravitational effects are expected to become significant. At these scales, spacetime may be granular or foamy rather than smooth, and the continuous Lorentz symmetry that enforces the speed limit may be only approximately preserved. Loop quantum gravity is one of the leading candidates for a quantum theory of gravity. In loop quantum gravity, the fundamental entities of spacetime are not points or curves, but discrete loops of space, woven together into a spin network that evolves over time. The smooth spacetime of general relativity emerges from this discrete structure in the classical limit, much as the smooth surface of water emerges from the discrete molecular structure of H2O. At the Planck scale, the discrete nature of the underlying spin network becomes relevant, and deviations from the continuous Lorentz symmetry of classical spacetime are predicted. These deviations are typically parameterized as energy-dependent modifications to the dispersion relation of light, meaning that photons of different energies would travel at slightly different speeds. This prediction has been tested using observations of gamma-ray bursts. When a gamma-ray burst occurs in a distant galaxy, it releases photons across a wide range of energies nearly simultaneously. These photons then travel for billions of years before reaching Earth. if high-energy photons travel at slightly different speeds than low-energy photons because of quantum gravity effects on the dispersion relation, the high-energy and low-energy photons would arrive at Earth at slightly different times, with the difference accumulating over billions of light-years of travel. The Fermi Gamma-Ray Space Telescope has measured the arrival times of photons from gamma-ray bursts at different energies. The results show no detectable arrival time difference down to a precision that places strong lower bounds on the energy scale of any Lorentz symmetry violation. These bounds reach or exceed the Planck energy, essentially ruling out naive quantum gravity corrections to the speed of light from the simplest loop quantum gravity models. String theory, the other major candidate for quantum gravity, incorporates extra spatial dimensions beyond the three observable ones. The extra dimensions are typically compactified, curled up at scales comparable to the Planck length, and their presence has negligible effect at energies accessible to current particle accelerators. In string theory, the speed of light remains a fundamental constant of the theory, and Lorentz invariance is exactly preserved rather than approximately preserved. The prospects for faster-than-light travel within string theory are no better than in classical general relativity. Some speculative proposals invoke specific features of quantum gravity to enable faster-than-light travel. Quantum tunneling, the phenomenon by which quantum particles pass through energy barriers that classical physics forbids, has been proposed as a mechanism for superluminal signal transmission. Measurements of the tunneling time of photons through barriers conducted in the 1990s by Günter Nimtz and collaborators appeared to show photons arriving at a detector faster than they would have arrived if travelling through free space rather than the barrier. This seemed to suggest superluminal propagation. However, subsequent analysis showed that the apparent superluminal effect is a consequence of the mathematical properties of barrier transmission for wave packets. The peak of the transmitted wave packet emerges from the barrier before the peak of the incident wave packet would have reached the exit. But no information is transmitted faster than light, because the wavefront of the transmitted packet, which carries the actual information about the signal's existence, never exceeds light speed. The tunneling result is a subtle but real quantum phenomenon that does not violate causality. The honest conclusion about quantum gravity and the speed limit is that no current theory of quantum gravity provides a physically plausible mechanism for faster-than-light travel. The existing experimental bounds on Lorentz symmetry violation are very strong, essentially ruling out the leading quantum gravity candidate's simplest predictions for superluminal effects. A future theory of quantum gravity might reveal new possibilities, but it might equally well reinforce the speed limit more firmly than classical relativity does. The unknown nature of quantum gravity is not a basis for optimism about faster-than-light travel. It is simply an unknown. So what is actually out there beyond the limit? After 10 chapters establishing the absolute nature of the speed limit, the impossibility of reaching it through energy or fuel, the catastrophic particle hazards at near-light speed, the failure of proposed loopholes, and the likely irrelevance of quantum gravity as an escape route, it is worth stepping back and asking what the universe actually contains beyond the edge of the reachable. What lies in the regions that light can reach but matter cannot? What are the actual objects and structures that exist in the universe, whose closest members are accessible to observation but not to physical visitation on any timescale remotely relevant to human civilization? The observable universe has a radius of approximately 46.5 billion light-years. This is larger than the product of the speed of light and the age of the universe, 13.8 billion years, times the speed of light, because the universe has been expanding throughout the time that the most distant observable photons were traveling toward us, carrying those photons along with the expanding space, and allowing them to cover more distance than simple multiplication would suggest. The most distant objects we can observe are galaxies and quasars at redshifts approaching 20, seen as they appeared only a few 100 million years after the Big Bang. Within this observable volume, there are approximately 2 trillion galaxies. Each galaxy contains, on average, hundreds of billions of stars. The total number of stars in the observable universe is estimated at approximately 10 to the 24th power, 1 septillion. The total number of planets is comparable or larger, given that we now know from the Kepler mission that most stars have planetary systems. The fraction of those planets in the habitable zones of their host stars, where liquid water could exist on the surface, is estimated at between 5 and 40 billion in our galaxy alone. None of these objects are reachable. The nearest star to the Sun, Proxima Centauri, at 4.24 light-years, would take Voyager 1 approximately 73,000 years to reach at its current velocity. At 99% of light speed, the journey would take slightly more than 4 years in Earth time and approximately 6.5 months in the traveller's proper time. This is the version of interstellar travel that popular science tends to focus on. A voyage that fits within a human lifetime in the traveller's frame, even if years or decades pass on Earth. But achieving 99% of light speed requires the energy and fuel resources discussed in previous chapters, which lie many orders of magnitude beyond current human capability. The Andromeda Galaxy, the nearest large galaxy to our own Milky Way at approximately 2.537 million light-years, would take approximately 2.54 million years in Earth time to reach at 99% of light speed, during which the traveller would age approximately 358,000 years. This is far beyond a human lifetime, even in the traveller's frame. To make an intergalactic journey fit within a human lifetime in the traveller's frame would require velocities extremely close to the speed of light, with Lorentz factors of tens of thousands or more. The energy and fuel requirements at such Lorentz factors are so extreme that they exceed anything discussable in terms of current physics without invoking exotic matter or technologies that are purely speculative. The universe is therefore vast in a very particular sense. It is vast enough that even at the maximum speed permitted by physics, travelling to most of it would take longer than the current age of the universe. The observable universe's diameter of 93 billion light-years, at 99% the speed of light, would take approximately 93 billion years to traverse in Earth time, roughly 6 times the current age of the universe. Long before such a journey could be completed, the Sun would have exhausted its hydrogen, swelled to a red giant, and died. Earth would be uninhabitable. Human civilization, if it survived at all in some form, would be unrecognizable. And yet the universe is observable in its entirety. Photons from the cosmic microwave background, emitted 380,000 years after the Big Bang from regions now 46 billion light-years away, have been travelling toward Earth ever since and have arrived to be measured by the Planck satellite with extraordinary precision. The information carried by these photons about the temperature and density fluctuations of the primordial plasma gives us a detailed picture of the universe's infancy. Telescopes detect light from galaxies more than 13 billion light-years away, showing us objects as they were when the universe was less than 1 billion years old. The speed of light, which makes physical travel to the distant universe impossible, simultaneously makes astronomical observation of the distant universe possible. Light from every corner of the observable universe has been arriving at Earth throughout its history, building up a record of the universe's contents and evolution. This is the peculiar situation that the speed of light creates. It sets a limit on physical travel that makes the overwhelming majority of the universe unreachable. But it does not set a limit on observation, because the observation happens using the very entity that defines the limit. We can see the universe in its entirety up to the observable horizon. We can measure its contents, trace its history, and map its structure. We simply cannot go there. The universe presents itself as an infinite museum that we can see in full detail from one spot, but can never walk through. The question of what lies beyond the observable horizon, the regions from which light has not had time to reach us since the Big Bang, is in principle unanswerable. These regions exist, assuming the universe is not finite on scales comparable to the observable volume. The physics of the universe presumably continues to operate there with the same laws and constants as in our observable region, since those laws and constants appear to be uniform throughout the observable universe. But we can never receive information from those regions, and they can never receive information from us, because the expansion of the universe ensures that light from beyond the horizon will never reach our location, and light from our location will never reach the regions beyond the horizon. The observable universe is our permanent, irremovable cosmic address. So what is actually out there beyond the limit is not emptiness, not a boundary wall, not some edge where reality stops. It is more of the same universe, continuing in every direction, structured, evolving, and filled with objects that are as real as anything in our immediate cosmic neighborhood, but permanently out of reach. Beyond the scale of individual galaxies like the Milky Way or Andromeda Galaxy, matter in the universe organizes itself into larger patterns. Galaxies cluster together under gravity, forming galaxy groups and clusters. These clusters, in turn, connect along vast filaments of matter, creating what cosmologists call the cosmic web. Between these filaments lie enormous voids, regions where very little matter exists at all. If you could step outside the observable universe and look back at it from some impossible vantage point, it would not appear uniform or random. It would look like a three-dimensional network, glowing strands of galaxies stretching across darkness, shaped by billions of years of gravitational evolution. The largest structures we can currently identify, such as the Hercules Corona Borealis Great Wall, extend across billions of light years. These are not objects in the traditional sense, but patterns in the distribution of matter, the imprint of initial density fluctuations amplified over cosmic time. They represent the upper limit of structure formation set by the age of the universe and the speed at which gravity can influence matter. And yet even these immense structures are just local features within the observable region. Beyond them, the pattern continues. What lies further out, past the galaxies we can currently observe at extreme redshifts, is a universe that is younger in appearance, but not fundamentally different in nature. The earliest galaxies we detect are small, irregular, and intensely active, forming stars at rates far higher than typical modern galaxies. They are seen during the epoch of rhyonisation, when the first generations of stars and quasars transform the intergalactic medium from neutral to ionized. But beyond the most distant of these observed objects lies an even earlier phase, one we infer rather than directly see. The time before the first stars, when the universe was filled with dark matter, hydrogen and helium, slowly collapsing under gravity into the first structures. Even deeper than this, at the edge of observability, is the afterglow of the Big Bang itself, the cosmic microwave background. This is not a collection of objects, but a surface in time, a snapshot of the universe when it first became transparent to radiation. It represents the limit of electromagnetic observation. Beyond it, the universe was opaque, a hot plasma through which light could not travel freely. In principle, other messengers like gravitational waves could carry information from even earlier times, potentially revealing the physics of the universe at fractions of a second after its beginning. But even these would not extend our reach indefinitely. There will always remain regions causally disconnected from us. One of the most counterintuitive aspects of this situation is that parts of the universe we can currently observe are already beyond the reach of any signal we could ever send, even at the speed of light. Due to cosmic expansion, there exists not just an observable horizon, but an event horizon. Galaxies beyond a certain distance are receding from us so quickly that any light we emit today will never reach them, no matter how long we wait. They are visible to us only because their light was emitted billions of years ago, when they were closer. In a very real sense, we are seeing objects that are already gone from our accessible universe. Over extremely long timescales, this effect will become more pronounced. As the expansion of the universe accelerates, driven by what we call dark energy, distant galaxies will continue to recede until their light is redshifted beyond detectability. Future observers, existing trillions of years from now, may find themselves in a universe where only their local group of galaxies remains visible, all evidence of the larger cosmic structure having faded beyond the horizon. The vast cosmic web we currently observe will no longer be accessible even to telescopes. This leads to a striking conclusion. The universe is not just spatially vast, it is temporally fleeting in what it reveals. We exist at a time when the observable universe is rich with information about its past and structure. We can see distant galaxies, measure the cosmic microwave background, and reconstruct the history of cosmic evolution. But this window is temporary. The same physical laws that allow us to observe the universe also ensure that much of it will eventually disappear from view. So beyond the limit lies a continuation without end, a universe that extends far past what we can ever access or influence. It contains more galaxies, more stars, more planets, and possibly more instances of life, arranged in structures both familiar and unimaginable. But the defining feature of these regions is not their content. It is their separation from us, enforced not by distance alone, but by the fundamental structure of space-time. The speed of light does not just limit how fast we can travel, it partitions reality itself, dividing the universe into what can be experienced, what can be observed, and what will remain forever beyond both. The speed limit is the universe. The speed of light is not a law that governs the universe from outside, the way traffic laws govern drivers on roads. It is a property of the universe itself, as intrinsic to space-time as the number of dimensions or the strength of gravity. It cannot be circumvented because circumventing it would require changing the structure of space-time, not finding a better engine. It cannot be exceeded because exceeding it would require existing in a state for which the mathematics of space-time has no description. It cannot be repealed or revised because it is not a rule imposed on space-time by some external authority. It is space-time expressed as a velocity. The experimental case for the speed limit is the strongest case that exists for any physical fact. Every atomic clock ever flown has confirmed time dilation. Every particle accelerator ever built has confirmed relativistic momentum and energy. Every GPS satellite in orbit has confirmed the combined predictions of special and general relativity to precisions of parts per billion. Every observation of cosmic ray muons has confirmed their time-dilated survival. Every collision at the Large Hadron Collider has confirmed the relativistic energy-mass relationship. Trillions of data points from dozens of independent experimental programs have never, not once, produced a result inconsistent with special relativity's predictions about the speed limit and its consequences. This does not mean physics is finished or that the speed limit is the final word on the structure of reality. Quantum gravity, still unformulated as a complete theory, may reveal aspects of space-time at the Planck scale that are not captured by special or general relativity. But the existing experimental bounds on deviations from the speed limit at accessible energy scales are extraordinarily tight. Any violation of Lorentz symmetry, the technical name for the symmetry that enforces the speed limit, must occur at energy scales so far beyond current particle physics that its effects at ordinary energies would be completely undetectable. And if the violation is undetectable, it is of no practical use for faster-than-light travel, even in principle. The appropriate response to the speed limit is not frustration at a barrier, but appreciation for what the barrier implies. The universe has a definite causal structure because of the speed limit. Events have a definite temporal ordering within the constraints of relativity because of the speed limit. Matter exists as a coherent phenomenon rather than dissolving into instantaneous interactions at arbitrary distances because of the speed limit. The speed limit is not a cage, it is the architecture of reality, the framework within which matter, energy, time and causality are able to exist and interact in a coherent and structured way. The restriction is absolute, and the restriction is not arbitrary. It is, as every chapter of this script has explored from a different angle, the necessary consequence of the universe having a coherent, causal, mathematically consistent structure. A universe without the speed limit would be a universe in which cause and effect could be reversed, in which the distinction between past and future was arbitrary, in which quantum mechanics would be inconsistent, and in which the notion of a physical law would lose its meaning. The speed limit is the price of a comprehensible universe. It is a price that, on reflection, seems remarkably low. What is this then? The title of this video promised a paradox. The paradox is not that something travels faster than light. Nothing does. The paradox is that the universe, governed by an absolute speed limit that cannot be broken, is simultaneously transparent to observation in all directions to the limits of the observable horizon, while being physically inaccessible beyond the nearest handful of star systems. The universe shows us everything and lets us touch almost nothing. The speed limit is both the reason for this frustrating limitation and the reason for the extraordinary richness of what we can see. Understanding that both things follow from the same source, from the geometry of space-time written in the constancy of the speed of light, is the real answer to the question the title asks. So what is this? It is the universe, and it is exactly as strange as it should be.